गिर गया क्या?
अरे नहीं रे, I was adjusting my chair.
ओके.
Please stop me if you all get bored. Nothing to be like compulsion to listen to me if I make you bored.
No,
Chintan won't be
Please
bored.
explain the math. Please explain the math behind
Yeah,
it.
हाँ.
that is the whole point I asked because I've like have I have 10 slides explaining the math only. So
Okay,
yeah,
perfect. I was so excited for this, to be honest. Like, it's gonna be fun. It's gonna be fun.
but even all those like all the slides I put for math, even they are not like suffice. I have to like just okay, this thing does that, and actually calculating that is a lot of time, like consuming a lot of time. So you just use code or some like Einstein Pi to calculate
Mhm.
it. You don't do it by hand. All the stuff. Yeah,
Explain as much as you can.
yeah. I'll try my
Yeah.
best.
All right. Cool.
Mm, I guess I can present. Just let me know if you can see the screen. Yeah, I, I guess. Saurabh, you can see the screen now.
Yes.
We should start now, Jay. Yeah. Yep. Yep. Yep.
I'm gonna leave and I'm gonna join from my laptop because it's easier to see the slides. So wait for me, please.
Yeah. 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 Okay. Okay. Just what else? Yeah. Yeah. So I guess I hope you can like hear me and see my screen as well.
Yes.
Yeah. So let's start. So before going to the like let directly jumping into a wormhole or some like black hole, we should know like the basic equations which govern it, like which describe it. So this is the Einstein field equations, and the only reason I'm saying equation is because it is not one equation. There are 16 equations in it, coupled in it, and basically you can see the subscript. These are all written in tensors form. So for someone like who don't know tensor, let's not get into very much depth into details of tensor. But for like just for description, I'll say they are set of numbers expressed as matrix in the matrix form. But you'll get like why they are very important and why like they describe this whole phenomena, like basically the curvature of space-time, everything. So let me just like so here this is R mu nu. It is a Ricci tensor we call it. This is the scalar curvature. This is what I can say. the metric tensor, cosmological constant. We'll understand this separately, like what it is and why it is important, what does it describe. But even going to that, before we should know some very basic concept about general relativity. So first of them is like space and time are like they. You can imagine space-time fabric. When we say space-time fabric, time is also blended with the three spatial coordinates. So it is like just imagine a sheet and you place some heavy object on that sheet, it gets curved. So that is just a very simple definition of what space-time is. Basically, due to presence of mass, energy, or matter, it gets bent. And the way it gets deformed, that we'll calculate afterwards. So that is this like we cannot spend very much time into it. Like we can go into very much details like manifolds, hypersurface, but that is all not very much important right now because it will be too much math. Yeah. So one of the very big, general idea which we need right now, because we will be talking a lot in terms of basis vector. So you might have written vectors like 3i, 3i, 5j, 6k, whatever. So that ijk is the basis vector. And from this diagram, like I don't think I need to explain anything like what a basis vector is. So basically, if this 2j, if you are like a vector, so j is the basis vector, 2 is the component of the vector. It would be a lot easier if I can just like write down, but let's you write a vector v expressed as 3i 2j, this much only. So the 2 is one of the component and I or and j are the basis vector of it. So that is just what a basis vector is. Uh, Okay, so now geodesic. So like, what is geodesic? What is a world line? So we should know all these things. So basically, when you are considering a fabric of space-time, or when you in general relativity, or even in like special relativity, nothing is stationary. You yourself right now are moving. If you're stationary, it is with respect to space-time, with spatial coordinates. But you are always moving forward in time. If I plot your world line, so you are always moving forward in time. So if now let's say if you are moving really, like if you're really having a motion, like not just in time but also spatial motion, so the velocity will obviously, velocity is a vector quantity, so it will give you the direction where in which direction you are now. What basically what geodesic is, now if I know the evolution of this velocity, basically how the velocity is going to change throughout like through the future, like for let's say after this many times, I can plot the trajectory, and that knowing a velocity at a particular instant, using that I can predict the future trajectory, and that's what we call geodesics. And in our universe, each and every single particle, light itself follows a geodesic, and basically they are the paths which are traced out by us. So if a satellite is orbiting around the earth, it is tracing a geodesic. So that and to give another more example, you must have seen a globe, okay, a globe on which the lines of latitude and longitudes are given. So that are just geodesics. So that is what geodesics is. And in our universe, if we consider not any forces involved, they are always straight. Light always travel in a straight line. And like many people say, around a black hole, light gets bent. Light never bends. Light never ever bends. Light can never bend. It has no mass. It do has energy, but even then, a black hole, even a black hole can't make the light bend. Then how does light follows a curved trajectory? It is basically the space itself is curved, and the geodesic it follows are drawn on that space. So it feels like light is bending, but in real life, light is never bending. So just imagine a globe is there, and a plane is moving straight. Okay, a plane is moving straight on a globe. So on a globe, it will look to you as it is moving like in a circle, a great circle basically. But if you flat out that thing, basically when you change the coordinate system, it is just a straight line. So that is what it is. So the trajectory which we see is on the like you can call it an illusion because it's just due to the coordinate system we are considering. So now Christoffel symbols, I know like no one knows about it if you're not into GR. But so basically, I told you a formula in which you can express velocity and like velocity as the change in its component and the basis vector. So in generally, basis vector do not change. Like on Earth, basically, it does not change. But a fabric of space-time, it can really change. And how to imagine a change in the basis vector is just imagine a graph paper. So all the grids, the small squares are all of equal length, like they all have the same dimension. But let's say it was elastic in nature, you stretch it, so they might change. And given like let's say they don't change at the same way, like one grid is bigger, one grid is longer, something like that. So that is why you need Christoffel symbols. What Christoffel symbol will tell us, basically it gives us how the basis vector change and with respect to our coordinate system. So you can see, so this thing, a red vector. So due to the change in the the grid or the fabric of space-time, you call it for simplicity, it has been moved here. So this vector is expressed as a Christoffel symbol, and we put it into the equation, and like all that mathematical integrity would be, it is not very difficult, but I cannot put all the mathematics on a slide, so I've just put up a main equation. So this is acceleration, basically how velocity changes as t is the proper time, so how it changes, and this is the Christoffel symbol. And this equation basically gives us the evolution of our basis vector with respect to time, how they change. Now, like all these things will just help you to look at points on a space-time, like this point, this point. But even right now, we don't have any measure of the distances. Like, okay, you got the Christoffel symbol. You know, you can calculate the change in velocity, but how do you calculate the Christoffel symbol itself? It is also a set of number. It is a like tensor only. Like, but how do you go about calculating Christoffel symbol? So this is where the most powerful tool ever invented in general relativity comes into picture, metric tensor. And it is everywhere. It is in the simplest calculation from the birth of general relativity. If you start learning, it would be the first equation I think you'll see in a book. And it goes all the way to the Einstein's field equation. A metric tensor, it is a very powerful tool. Basically, you consider the Pythagoras theorem. Like if you want to calculate distance between 2 points, you form a triangle and you just calculate the distance, as simple as it gets. But that is not always the case. If that is when you use Pythagoras theorem that easily, the form which we used in school is when it forms an orthonormal basis. The axes are perpendicular to each other. If the coordinate system itself we are considering is stretched or is like at a different inclination, the Pythagoras theorem won't work. So this is you can express the square of any quantity, any distance, like by the combination, all the possible combination of two sides. So basically this is that, and this A, B, C are some random numbers just generated out of nowhere, and these numbers form the metric tensor. So if I consider a two-dimensional space, it would be a 2 cross 2 matrix. So what happens for the Pythagoras theorem is B goes to 0, C goes to 0. So you have A is 1 and this D is 1. So you have side 1 square, side 0 square plus side 1 square. So that is how a Pythagoras theorem comes into picture. Even these quantities are there in the Pythagoras theorem, but just that the constant, the components of the metric tensor goes to 0. That's why these two combinations never occur. But we are more interested in a 4-dimensional case. So it is written like this. Metric tensor, it is going to be a 4 cross 4 matrix. I know it looks scary, but it is very powerful. It is very powerful too. Like it literally is going to tell you how you can, like how your grid, the shape of the grid itself is. Yeah. So yeah, metric tensor, as I told, it is a very important tool. With the help of metric tensor, you can, like, as I told you, there are, as far as now we were measuring changes in the basis vector at different points, but you still don't know the distance between those 2 points. So how do you calculate distance, angles? All this is with the help of metric tensor. And how it is a bit of math, but not that much, but we'll not go into very much detail of math, but for us, it is right now, this much is important, that metric tensor help us to calculate the Christoffel symbol, which will eventually help us to calculate how the basis vector change. And yeah, that's how we calculate that. So basis vector help, the metric tensor helps us Christoffel symbol. Christoffel symbol helps us calculating the change in the basis vector along with the proper time as our motion goes by. So that's how it is related. So to give like a proper view, just so basis vector are directly related to the grid. So just for this thing, if you have graph paper, just stretch it. Like if you can stretch the graph paper, obviously, then you'll see the grids will get changed, the small square will get changed. So that is governed by the basis vector. So in space-time, when you consider a motion of, let's say, an object, its basis vector can change, the component of the vectors can change, but a vector as a whole will always remain constant. The value it's corresponding won't change. It's just the basis vector and the components. That vector as a whole will always remains constant. So this is a bit important to know. I know I'm going very fast, but like general relativity cannot be explained in 1 hour. It's impossible. So yeah, so basis vector directly related to the grid. Now the shape of the grid is expressed through metric tensor, as I told you. So you have to calculate metric tensor for the like if you want to know more about the grid. So by measuring metric tensor, you can determine how that basis vector change because you put then you can calculate the Christopher symbol. So this is the formula of the Christopher symbol. Cool, we know everything. So basically now we have all the tools. So if you know the Christopher symbol, you know the metric tensor, you can plot a trajectory. Basically, you put that into a geodesic equation. You can just plot a trajectory of an object through space-time, just dependent on the geometry of the space-time, nothing else. So you do that. But as we had a problem last time, not last time, like when we considered Christopher symbol, how do we calculate Christopher symbol? Through metric tensor. But how do you calculate metric tensor itself? There is something even more to calculating metric tensor. That is the Riemann curvature tensor. So to understand this, I think we should just do a simple activity. I know it's very basic, but still doing it will like give us a very good example of what it is. So like if you all can just take a paper out, I can show, but I don't know how much good visibility it would be. So yeah, I'll just share a paper from my book. So if this represents our space time, and if I draw a straight line on it, okay, it's not perfectly straight, but it's straight. So this is very simple, very simple thing. You can see the straight line. If this thing is bent like this, you see the trajectory also gets bent. This is very simple, but this is not what curvature, like this is not how I will define curvature. This is very bad representation. So to do that in the vector form, like you have all seen a globe, right? Let me just we'll just see the globe itself. Okay, let's not go there. How a globe is. So you have the lines of longitude, you have the lines of latitude. So all that are not squares basically. The thing forms, they are not of all equal length like we have on a 2D sheet. So here, I don't know how I'll show this, but yeah, can you see this thing? Like in the orange, a square, and basically this is, I know it not exactly looks like cut from a globe, but my drawing is bad, so please bear with me. You can see the square perfectly. Saurabh, can you see it properly?
Chintan,
Yeah.
I guess it
It's
would be
blurred.
better visible if you remove the blur around you.
Right. Wait, I'll just show this through this like phone, so then I can show it better. So I'll mute in case it just goes. Okay. There is. You can hear me now?
Yeah.
Uh, but is there an echo?
No, there is not an echo.
You're on mute.
Okay.
There is an echo now.
Now it won't be. Okay, I'll remove the blur. Where is the blur? Uh, I'll fill myself so I can also see what I'm showing. Okay, now can you see this two shapes? What the hell?
Yes.
Yeah. So now what I'm gonna do is like okay. So this is my one vector. Okay, this is my one vector, and basically this is my grid. So now I transport my vector to here. So it would be basically you can assume this is a geodesic. So it forms here. Now I transport it here, like along this line. So the orientation of my vector is same. So now I do a reverse thing. So first I transfer it here. It comes here. Now I transfer it here. So the orientation of the vector basically has not changed in this case. But now let's see what happens if we do it through this thing, a kind of a curved thing. So now it is going to follow geodesic. So it's going to end up pointing here. Now I transfer it here, so its end orientation will be. Okay, I don't know why this pen is not working.
चिंतन चिंतन ऐसा हो सकता है हम लोग कि if we are thinking of the position of the vector along the geodesic, will it be sort of tangential in a way?
What was I didn't hear?
If I consider let's say if I imagine the Earth revolving around the sun, sort of. So if I'm basically thinking of that as the position vector, can I think of it like how you're trying to explain कि the orientation is not really changing? So हम लोग बोल सकते हैं, is it the tangent or like is the vector that you're trying to explain tangential in a way or a circular path?
It is like tangential, but like I want to point out the difference basically at the end, like in the two transformation, which end. So tangential would be like just one component. I need two components. That is why like I have to do this. Otherwise, I'll just say that. Is there some? I know, but I don't think I would be able to draw that good. But let me just try. But how I will draw symmetric objects over here? Dude, that's the problem, no? Otherwise, I would have drawn. Like, it would be difficult to draw straight, because the symmetry is what I'm trying to show. This is clear now?
You can draw straight lines. There is
Okay.
option like shift and then hold the mouse pad and drag.
So the thing is, this is my mouse. I don't have a mouse with me right now, so I'm using that laptop thing, so I don't know. I'll try this way if you can see. So I'm transferring my vector through this trajectory. It goes here. So then I just transfer it here. It comes here. So now I'll do the another way, like here I transferred here and here. So it goes here, and now it ends up like this way. It comes here. So basically, you can see the orientation of the vector is not same. So this much is the difference, and difference is what we are interested into. So that difference, the difference in the orientation of two vectors, is expressed by the Riemann curvature tensor. So we'll go to the Riemann curvature tensor now. Just a minute. Yeah, you can see my screen, right?
Yes.
Yeah, it's clear.
Yeah. Now I understand how much problem teachers faces when they're teaching. Yeah. Okay. Yeah. So this is like that thing was the difference basically was the Riemann curvature tensor, and this is how you calculate it. It is not very difficult to arrive at this equation. It's very simple. You just do some substitution. I can share after that. Like it's very simple. You come around here, but here is where we get problem. So basically, set of all these is going to tell us how our basically everything how the because the curvature is represented by the like change in the grid, basically how it would change. Everything is encoded in this Riemann curvature tensor, because we just saw the more the object would be curved, that the more the symmetry would be disturbed. Like basically you won't get the two vectors aligned. It was just for representation to imagine symmetry. It's not always like vector, but yeah. So more the two vectors will be disaligned, or the symmetry would be disturbed. So more is that more the curvature, the more is that difference. So the now there is one problem with Riemann curvature tensor. So it has 16 components in two-dimensional space. Okay, nothing, you calculate it. But when you go around in a four-dimensional space, like a real space, it has 256 components. How? Mathematics, but it gets very difficult to calculate all those 256 components one by one, one by one. Most of the components goes to zero. Some are because you following the same trajectory, but even then you have to calculate all to know which ones are zero. So basically that Einstein field equation is a set of 16 equations, but 6 equations like are either similar or they goes to zero. So we have 10 basic equations for the Einstein field equation. So one more thing. So now you need the Ricci tensor and the Riemann curvature scalar to calculate the Riemannian curvature tensor. This is the last thing. After this, we don't need anything else to calculate Ricci tensor and Riemann curvature scalar, or a Ricci scalar. Sorry, it is called a Ricci scalar. I said it, Riemann curvature scalar, I think. So yeah, so you use Ricci tensor and Ricci scalar basically to calculate the Riemann curvature tensor. Both of them, you can think of it as a component of the Riemann curvature tensor. There is a descriptive method how you calculate. Sorry for that disturbance. So there is a method how you calculate Ricci tensor from the Riemann curvature tensor. There is a lot of mathematics. That thing is difficult. Calculating Ricci tensor from Riemann gets tedious if you are doing it by hand. Obviously, with the computer, it's very simple. So okay, I think I just skipped one slide. I think no, but yeah, this was one. So the array, man, I don't know why it always does this. Shouldn't have two transitions. So yeah, so with this thing, the right hand side of the equation is done. Basically, T is the stress, T mu nu you saw in that equation is the stress energy tensor. It gives you the distribution of matter and energy inside a space we are considering. We'll not go into the details of it because the case which I studied, the Schwarzschild spacetime in that T goes to zero. So we are not bothering with it right now, but obviously it becomes very important when you're talking about a Kerr black hole or a Kerr-Newman black hole. So yeah, so finally the good stuff is here. We have done with all the mathematical integrity or the boring stuff if someone feels like it, but I find it very interesting even this math, even though I'm not good at math, but yeah. So where do you find a wormhole? A wormhole is not a separate thing, at least the Einstein-Rosen bridge, the way it is described in Schwarzschild spacetime. So it is like a black hole. You enter a black hole. This black hole singularity is not the end. Basically, that path leads you to another thing, to the another universe, something else, somewhere else. We'll see where it leads us to. But before that, we need a map. Like wherever we are going somewhere, we do need a map. Like you need to know the proper description of it. So this is our map. This is the Schwarzschild metric. This both are the same thing. The only thing is which equation? Wait a minute. Yeah, where RS? Yeah. This is written in the terms of Schwarzschild radius. Basically, that's the event horizon basically of the Schwarzschild black hole. So this both equation are one and the same. So this equation is a solution to Einstein's field equation, and this equation is the one which tells us that a black hole, an object like black hole existed. Basically, Schwarzschild spacetime is a flat spacetime. Okay, everywhere. Calculation for Schwarzschild spacetime is very easy compared to Kerr because the Ricci tensor, the metric tensor goes to zero. So all other things, because metric tensor, with the help of it, you calculate Christopher symbol, so it goes to zero. The Ricci tensor goes to zero. So ultimately, Riemann curvature tensor goes to zero. So I didn't have to deal with a lot of that because if I would have calculated for Kerr, I would have to calculate for all those components. But it goes to zero everywhere, but a point that is a singularity. There you can actually evaluate the Ricci tensor for the Schwarzschild black hole. So this is the Schwarzschild metric. If I tell you what assumptions Schwarzschild make, it would be like I'll tell you afterwards because that's more fun that way. So here is where the importance of coordinate systems comes into picture. So first of all, Schwarzschild metric can work very well inside the black hole. You can trace the trajectory of the particle, that ds square, basically the trajectory of the particle, even inside a black hole. But we do have a problem. Schwarzschild metric ends basically at the event horizon. The event horizon is a coordinate singularity for the Schwarzschild black hole, Schwarzschild metric. Why is it a coordinate singularity? Because Schwarzschild metric is defined in a term of an observer who is observing the black hole from infinity or from a very far distance. So if I'm observing, let's say any one of you, let's consider Saurabh. If let's say Saurabh is falling into a black hole and I'm observing from very far away. So Schwarzschild metric is described with my perspective, my frame of reference. So Saurabh is plunging into the black hole. Once he crosses the event horizon, I wouldn't see him crossing the event horizon. The time would kind of freeze for me at the event horizon. So I never see Saurabh crossing the event horizon. So basically, that thing is kind of a coordinate singularity. Even at the, if you consider a globe on the top, the North Pole and the South Pole, all the geodesics meet. And that is what we call a coordinate singularity. But a coordinate singularity is not a true singularity. For me, okay, it is a singularity. Basically, I cannot see what's happening away, like after the event horizon, but Saurabh can see. With terms of Saurabh, pretty much everything is going normal, not in that normal. Basically, he might die, but yeah. So he's falling into that black hole. So for him, still you can trace a trajectory. So this is where we do something called as coordinate transformation. So the train horn, okay, I'll just wait. Yes. So we change our coordinate, we transform our coordinates basically to change the perspective from that observer. So we use something called as a Eddington-Finkelstein coordinates, which basically removes that singularity, the coordinate singularity. Basically, it is a pseudo singularity. It's not a true singularity. So it removes that. Basically, it's kind of, if you want to think it physically, not mathematically, it just changes your perspective. And now for creating the map, as I told you, we need a map. So we use the Kruskal-Zakaris coordinates. Now this thing is mind-blowing, really, because when we plot the Kruskal-Zakaris diagram on a, like, the resulting map is called the Penrose diagram, Carter-Penrose diagram, we see something very interesting. And even people say like, it is just not possible, but this is mind-blowing stuff. We'll just see what it is. So this is the figure B, basically, where it is written curvature. So curvature singularity R is equal to 0 is the Penrose diagram. So the region 1, M1 is defining our universe, basically our universe. This is a black hole, and the Kruskal-Zakaris coordinates are in like given in that way. It is 45 degrees path. You can see basically this line is a 45-degree line. Okay, I'll just use a highlighter if I can. Yeah. Okay, yeah. So this line, which is this thing, is the singularity of the black hole. This thing is the event horizon of the black hole. This is our region, and this is black hole. So this much Kruskal-Zakaris diagram was. But then we plotted it on a better diagram, Penrose diagram. Basically, this is the future cosmic horizon. This is the past cosmic horizon. From the light cone, you know that stuff. We are not interested in that stuff. The thing we are interested in is these two regions, basically. So this is the event horizon. So looking at this diagram, one thing we should know about geodesics, I should have mentioned it, geodesics should always be complete. You should have a definite origin of from where the geodesics are arriving. Otherwise, you can't say that diagram complete, or you have to trace it back. So if you cross the event horizon, let's say this thing, okay, you go into the black hole and then you eventually move toward the singularity. So the light coming from here, basically infinity to here, you can have an origin. The light which is coming from, let's say, inside the black hole, you have origin. But what about the light which escapes from here and goes here? Or what about this region? You don't have anything here. You don't know what it is. So this diagram was called geodesically incomplete because we don't have definite origins or where the light is coming from or where the light is heading. So we didn't know about this region. So that was an incomplete diagram. This is called as the maximally extended Carter-Penrose diagram. So here we get a complete view, and now we have these two new regions which have appeared here. So this yellow region is called the white hole, and for white hole something very special happens. Time runs backwardly for a white hole, so it seems like you are thrown away from the singularity, from the event horizon. You don't stay there. It behaves in an opposite manner to a black hole. That is because it is on the negative axis. It is a coordinate reflection of the black hole, so it behaves inversely. So is this universe, M3. It is a parallel universe, kind of a mirror image of our universe. So all those light rays which didn't have any origin before are here. So basically the light rays which are going here ends up into the parallel universe. You go in here, if you go here, you end up into a white hole, which will eventually throw you into the parallel universe only. So yeah, that is how, so this traveling, you just traveled. That was the Einstein-Rosen bridge you traveled, like crossing this path, or going from here to here, or crossing all these singularities, all this event horizon or the boundary. But here is where we have a problem. Okay, all the paths which I shown you to travel into the another region, basically from M1 to M2. Let me just go back. So yeah, going from M1 to M2 is very simple, but you will go into a black hole pretty normal. Just go there. But if you have to go into this region, if you want to from inside the black hole, if you want to like escape its gravitational influence, obviously you have to travel faster than the speed of light. That is where things get tricky. You to cross the Einstein-Rosen bridge, to cross any of this region, to go like to access the region M3 and M4, you have to travel faster than the speed of light. Only superluminous speed will take you there. Otherwise, you can't go there. So let's just consider you're falling into a black hole. So within a black hole, something very intriguing happens. So time and the coordinates of time and space, they inverse, they get changed. Basically, what I mean when when they get changed is basically normally you have time running only like in one direction, and space is like you can access in both the region. But due to the infinite gravitational pull, the curvature, which is due to the singular point that's infinite, not infinite, but a very heavy mass, space is like dragged to that singularity at speed faster than the light. So now you can travel, like the time axis becomes traversable in both direction, but the space axis, the spatial coordinate is just going plunging down. You can't escape it. Obviously, if you travel faster than the speed of light, then you can. Yeah, so that is what I wanted to say here. So once inside the black hole, you now what would be your view? Obviously, there would be some light coming from behind you. There will be some light which is already inside the black hole, which is trying to escape, but eventually will fail. So it is kind of seeing the past of the black hole, and you'll see something very strange. Okay, you'll never reach the event horizon. Sorry, why I say event horizon? You'll never reach the singularity because that region of space is infinitely curved. And if before reaching there only you will die. But let's say you can travel faster than the speed of light, then you have two paths left. All these assumptions has to be made because so let's say you are in the region M2. So now you have two paths left. You are eventually moving towards this line, which is the singularity. So you can turn around, you can go here, like just come out from the black hole with superluminous speed, or you can just go here. That will take you to the another universe. So yeah, that was it. Einstein-Rosen bridge. We just crossed the Einstein-Rosen bridge. But that is where the difficulty comes. The Einstein-Rosen bridge always requires a superluminous speed. And now what is a wormhole? We'll come back to why it is failing or why you cannot traverse the wormhole very quickly. So the gravitational hole, as I mentioned, according to the Schwarzschild metric solution, it is not the end. It is not the dead end. Basically, you have a two-sided funnel. I do have plots you will be able to see. So it opens, like passing through it, you end up into one more region. And that funnel, which is connecting the two regions of space-time itself, is called as a wormhole. But according to the original idea, the ER, Einstein-Rosen bridge, was supposed to connect parallel universes only, as we saw on the Penrose diagram. But there were these two people, after a very long time of the field equation and Schwarzschild solution came, they would hypothesized, and even I think they had a mathematical proof that does not necessarily mean to happen. You can actually travel through the same universe using Einstein-Rosen bridge. You don't have to always connect parallel universes. And how it went, it might be tricky. And even they realized this could lead to time travel. How it could lead to time travel? Let's say you have two basically a black hole, basically, from which a wormhole is like you can pass through it. And the one end is this end is basically rotating very fast. Not rotating, like black hole itself is not rotating, but that thing is moving faster, like at the speed of light. So if I am this black hole, like if I'm standing on this black hole and this black hole is rotating, moving with the speed of light. So for me, time dilation basically for that thing, pretty much everything is going normal but the time would kind of freeze for this black hole, which is rotating, revolving very fast with respect to the first one. Okay, it is always important. The time dilation, all these things always happens with respect to someone. For someone who is moving at very high speed, for him the time is going proper only. That is called it's his proper or her proper time. So it is when with respect to with someone, like with the frame of reference of someone, it gets like that effect is visualized. So now this is some stuff which I did. I don't want to explain this all because it is a bit mathematical, but yeah. So I plot the hypersurface. So what a hypersurface is, it's basically from a manifold. Let's say I have a manifold of n dimension, a space of n dimension, and I cut out a slice of it, like n minus 1 dimension. If I have 3 dimension, I just cut out a slice of 2 dimension. So that thing is called a hypersurface, and this is plotted. This all are the hypersurface trajectories. And now this is at a particular time instant, t is equals to 2, t is equals to 1.5. There are all particular time instances. And this is pretty much that only, the coordinate, not the coordinate, the true singularity of the black hole. So this much is clear. We won't go into the details of this, but something very important observation you should make is these lines are complete. Why do these lines are not? Like why you don't have a horizontal line even over here? Why not? That is what destroys our wormhole. So this is for t is equal to 0. Okay, please keep this diagram in picture. Like the I should have like plotted it side by side, but then okay. So let's observe for t is equal to 0. Okay, the wormhole is stable. So if you freeze the time, then like if you just assume time is t is equal to 0, the time is frozen there. You can traverse the wormhole. It would be very easy then. Then you can pretty much traverse even at a like not a superluminal speed. You won't require. You can just traverse it. But why you need superluminal speed to cross the wormhole would we understand right now. Why subluminal speed won't cross a Schwarzschild wormhole. So then this is for as time is evolving. This is for t is equals to 0.9. Don't take it as seconds. It would happen really fast. This is just like for the coordinates, like for plotting. So this has reached almost the singularity. At singularity, the true singularity, the singularity of the black hole is the only point where the geodesics end. I told you geodesics need to have some definite origin. They end nowhere in the universe except at true singularities. And there are very few examples. I don't know about others, but one of the example is the event, the singularity of the black hole. That is where all the geodesics end. Done. So that is the reason I cannot have this. If this is a singularity, I cannot have geodesics beyond it. So yeah. So I've used something called as an isometric embedding to do all these things. And I pretty much found the code for it. I didn't do it myself, not good at coding. You all know that. Yeah. So then eventually with time, the funnel gets disconnected and the hopes of my hopes of living Milky Way ever are shattered, because even if you are traveling at the speed of light, you cannot traverse the wormhole which is described by Schwarzschild, because it collapses onto itself. Even before you cross it, who knows how much superluminal speed you would need to traverse such a wormhole? Would it be even stable? I don't think so. It would stay stable because it now, I got this because I did a lot of calculations, so it does make a lot of sense to me. But I know I just bombarded all the things I did to you in just, let's say, what time, 40 minutes or so, or half an hour. So I know it's difficult to digest, but yeah, that's the reality. So now let's say you get the freedom to travel with the speed of light as well, but you have one more problem. The black hole described by Schwarzschild is a non-rotating and an eternal black hole. Okay, let's say you find a rotating black hole as well, but the eternal word is very important. That black hole which is described by Schwarzschild black hole, it is not formed from star collapse. It's formed from always there. It was always there. That is what it is. That is the word eternal plays a very important role, because you don't find any black hole which does not have a spin parameter. It will always be rotating. It will always have some spin. But even if you find, there are possibilities you might find this a stationary black hole, but will that black hole will ever be eternal? Would it be like from the start of time? Basically, the moment time started, that black hole was there. That is the hypothesis of the Schwarzschild. So we are now never going to get such black holes. That does make sense, because where can you find such a black hole which was always there? Even the first black hole which was formed, the oldest one, the primordial ones, even they were formed after many years of the Big Bang, that if we consider Big Bang as a theory. So here is where our journey ends, basically, because we can't travel faster than this. Stupid shit I've written. I won't read that, but basically it's just saying that faster travel always leads to silly paradoxes, some paradoxes. Like you are kind of seeing someone falling into a black hole. He comes out in the another path, so you just saw him fall into a black hole, all this stuff. So it's kind of that. So faster than light travel is not only a very big imposition to general relativity, against general relativity, but it do leads to paradoxes which we cannot resolve. So that is the reason why faster than light travel is not possible. And some people believe that the white hole and the parallel universe are just mathematical objects, basically the coordinate reflection we need to complete the Penrose diagram. I'm not one of those, but they might be true, because like it does make sense. If you cannot find such a black hole which is described with a Schwarzschild, can you find the region which are described in the diagram? So that is, yeah. So hence the conclusion here is like the Schwarzschild black hole is not reversible. Stay in Milky Way, stay in solar system. You cannot go anywhere. So yeah, so that was a simple description which I can give. And thank you for like listening to my blah 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 blah. So this is just a photo. Like this were the few members from where we started the discussion club, and I'm really happy I'm still in touch with almost every one of them. So yeah, that was it for my like what I can say about saying and so much stuff. But yeah, so yeah, I'm done.
That was amazing.
Yeah. So now we can even consider the case of the black hole. I did study a bit, but I'm not very thorough with the Kerr black hole. And what I can say, I was just too tired and I didn't want it to make any more further presentation, because like I already, that was a huge presentation I had to make. So basically a wormhole is, even when you consider a Kerr black hole, a black hole which is spinning, even then there is something you need something called as a exotic matter to keep the throat of the wormhole open. Basically, the exotic matter is kind of a negative matter, which has negative energy density. So it would have kind of an anti-gravity which would push apart. Like gravity is trying to attract, and that exotic matter will repel the gravity. Finding such matter would obviously be very difficult if, like what I can say, finding such matter like exotic matter. I don't think such matter exists, but there is a practical proof to it. That is a very cool thing. We have a practical proof called as a Casimir effect. You put two plates, I didn't go into the detail, and you actually generate negative energy density between those two plates. They do some electrical, like it is related to electrodynamics. But then also that effect is produced at a very small scale, and that the plate also has a mass. So the positive energy density created by that plate, just the mass of the plate is very much larger than the negative energy density which is created between those two plates. So finding exotic matter is another problem. And a Kerr black hole, the map which I draw gets very large for the Kerr black hole. But even then we have a problem, we cannot navigate it. You would end up, let's say, in some another black hole. You can end up in some parallel universe. You can end up into our own universe. You have no way to predict where you end up if you consider the Kerr black hole. Something important about a Kerr black hole is ergosphere. Like it has another region called ergospheres, and there is inner event horizon, outer event. There is outer event horizon. All those things are there. And for Kerr black hole, the calculation becomes hell. The calculation becomes hell. I don't even want to show the calculation which I wrote, like which I had to go through. Basically, at a point, after some point, I was like, okay, I'll just find a solution and just paste that on there. I didn't even want to type the equation. That was like my experience. But after this, I fell into love with GR. I'm not good at math. Everyone knows I'm horrible at math. But I don't know why after doing this practical, I have always, now I'm attracted to that subject, because once you get to picture those things because now I can imagine Ricky tensor in my mind, what it does. Once you get to have a mathematical and even a like imagination of those things, this subject becomes so amazing, so amazing. And yeah, do study GR if you get opportunity. It is really fun. So that's what I wanted to say. I'll shut up. I spoke too much without any break.
Can I ask some questions?
I can try to answer. Yeah.
Yeah. So one thing is that it follows the geodesic equation. I thought the geodesic equation was a first order approximation. That I mean, because it doesn't consider back reaction. Like if I have two black holes, I wouldn't expect black hole number 2 to follow a geodesic, because it's just got too much mass. Like only maybe a photon would follow geodesic, but something else. I'm not sure. I don't think that's right. Is it?
No, everything, even a satellite, even the Earth which is moving, basically its trajectory itself is called a geodesic equation. And when I mention a geodesic is always straight, that is when there is no matter or no energy. But why a moon revolves in a circular or elliptical orbit? Because a mass of the Earth is present in that fabric of space-time. So every object in the universe, not only light, we describe the path of light not by geodesic. A proper term is a null geodesic. That's what we use for light, but the geodesic can be for anyone. If I want to throw this, I can have a geodesic for it through space-time. That is what geodesic can be used to trajectories of any object in the universe, entire everything. Not the space itself. Obviously, you can't have if you want to have a geodesic of expanding space, I don't think so. That could be done. I don't know about that thing, but every object you can have a geodesic. So now, yeah, this was a discussion club. So now you all can discuss, you all tell me what you think about it. That would be good. And I got a lot of help. Obviously my classmate helped me a lot to study this here and there, everywhere. Because without them, I couldn't do this. I'm dumb. I need help from people to study. And I'm really happy, I have such good classmates who always help. So, yeah.
Well, Chintan, you're definitely not dumb.
No, I am because
I mean, no. And secondly, if anybody wants to I used a certain resource when I wanted to study GR, because honestly my calculus is also pathetic at a point in time. So I used these lectures by this particular guy who teaches the mathematics of GR from scratch. He starts from 2D coordinates, goes on to do 3D coordinates, and then he kind of goes on into tensors and transformations and tensors and everything. So, I mean, one second. I'll just put up that link. So, I mean, since you mentioned, and I'm sorry I was late also to the meeting, you also mentioned that, the math is very complicated and everything. So, if anybody wants to follow up with the math, because we did this, we did all the, you also said all the equations, you must have really gone through the whole metric and got the solutions and everything. Okay, fine. So, I mean, for people, I don't know the population over here, anybody is doing the math or not, or I wouldn't do the math again, honestly speaking. I mean, I dropped cosmology because of that. Dropped in the sense, I did not pick up the subject. I did only the basics, which included this much. Care metrics with the pouches, I was like, forget it, I'm not going to do it. Mere bas ki baat nahi, this is not my thing. So I mean, I will just send, put up the link in this chat.
Yeah, in our chat, yeah. I'll use that.
Math. I don't have the playlist right now. I will send. I'll just paste it over here.
Yeah, whenever, you can even paste in that group. It is not in this meeting only. In our group.
Sure. So I'll put it on WhatsApp then.
Yeah.
Okay.
Yeah, there's a link I put of Physics Stack Exchange where someone's actually answering my question, which I said about the geodesic approximation. It is an approximation, and it's on Physics Stack Exchange. You can check it out. I put it on the chat.
So yeah, why it is called approximation, I'll tell you. So if you're considering a flat space-time, it would be a perfect thing. Because
no. I'm saying that what you're saying, ds square equal to 0, that's an approximation. It does it will hold. That
is an approximation, because then it is all related to the world line, the norm.
Yeah, that's called the geodesic. That is the geodesic equation.
If you're talking about that thing, then that is assumption. And that
is the geodesic equation as far as I know.
That, we should know about the norm of the velocity is always speed of light, all those stuff, which is not that much important. Because in this thing, but yeah, when you do sit and do the mathematics, then you'll have to consider that thing. But yeah. That is the right one. I thought you were talking about geodesic cannot describe someone else's trajectory.
No. And one more thing about the stuff you had said that about the Casimir effect. In QFT, you can define a 0-point energy anywhere. So there's no really negative energy there, right? I can you only measure potential differences. That's the whole game they play in renormalization. So.
Yeah.
So
I don't
technically,
know that much Casimir, but I don't do indeed. I just read it because I know that is
I think what you're saying about this, it's actually disputed whether negative energy can Like, I mean, because I can always put a plus C in classical physics to my potential energy and say that's my new potential. It's only in GR where you have zero torsion and it couples to the tensor that it makes a difference, because there you have absolute energy in GR, right?
Yeah, I'll have to see that Casimir effect because I just read it somewhere. Like even when I was doing for like preparing for the Viva of the project, I just read it. Okay, this is this. I didn't go into the details because I don't like that electrodynamics is and that stuff.
QFT,
But yeah,
bro.
yeah. What,
I mean, electrodynamics is nice. QFT is like what's going on.
so all those things, like it gets from there to there, then all those things, I was like, oh, just read because that is even then, I just read it. You do have thoda bahut negative energy density, but it is repelled hugely by the mass of the plate only.
Dude, that's what I'm you have in classical physics you have an energy, and then you can always like put a constant to plus a constant, right? Because you only measure potential difference. It's the same in QFT. So that's why I'm saying you can't really call it negative energy density.
Yeah, in a way, but if it is kind of repelling, if it is
it's not repelling. Even if you look
if
at the
it
equations,
is-
there's just more pressure on one side than there is the other. I can add a plus C on both sides and make it positive.
But that is a mathematical thing you are doing now. You are
No,
just
no,
adding
no.
plus C.
Yeah. I mean, in QFT, you throw out the ground state energy of the oscillators, bro.
That is okay.
The ground state energy is infinite, technically.
Yeah. So don't consider in that way. Like if so, just like imagine a chunk of matter and which is kind of like what I can say, avoiding the wormhole to collapse. What explanation you can give for it? It is because it is kind of behaving as an anti-gravity. It is pushing it. So you have to use that term. It is having negative energy density. I'm not talking about the mathematical integrity about because mathematically something might be this like explain something, but physically it can be very different. We just saw it with this thing like wormholes. Could mathematically it is not impossible, but we know practically such things won't be possible. So yeah, I don't know much about QFT, but yeah, I'll definitely look onto it. Like I don't know because I'm not read that much, but yeah.
I would like to talk a bit about negative energy. It is not something that I know about very much, but it is something I have read here and there. I guess negative energy is something that is not possible in this universe because the total energy is zero, but we can have it. We can make it possible somehow. Uh, through our equations, but I guess as like in far off in time, like not now but very far off in time, as universe expands to a very large extent, I think negative energy wouldn't be possible in that amount of
Are you talking about the
in-
cosmological constant?
I have no idea what I'm talking about because I don't know about this stuff. I'm still in bachelor's. So, but what I think, like basically, is that as we go further in time, negative energy won't be possible to that extent because universe has expanded very much. So the total energy is now lower. Total energy of the universe is now lower than what it was. So the negative energy, the possibility of having negative energy wouldn't be there. So we can say that having wormholes very later in the time of universe won't be possible.
Chetan, one thing I wanted to ask you, topologically, what does your stuff look like? Like, is it a Mobius strip or something? I'm just curious about that.
Which stuff?
The wormhole that you showed us, like, because you said space and time interchange, so it's like topologically non-trivial, right?
Yeah, and that would be like topologically, but it wouldn't like what I can say. What we call that word? Like it wouldn't violate anything. It does happen because the space is now flowing only in one direction. Only in one direction. That's the end. And we don't understand very well how time would kind of behave in that. But from that Penrose diagram, you can like have that vision like, yeah, space has now gone only in one direction, but what I can say, the time axis, the coordinate of times, they can like kind of traverse in both directions. So it wouldn't violate that thing, like the space should be smooth and all those things about the topology. It wouldn't violate that. But to picturize, it's kind of difficult. Like, would you, this thing I'm still not clear. Like, would you be like traveling, time travel just inside the black hole, or what? If you, it is
Yeah, because like I was thinking, like, so like we have so if space and time change, it's like the second law of thermodynamics would become, as you approach the black hole closer, your entropy would go higher, right? Because you've swapped space and time.
Yeah.
Usually it is so. So stuff like that is what I was wondering about. But okay.
Okay, any other questions?
Okay, yeah, one thing I had in my mind. So Chintan, like in the beginning, now you mentioned that light never bend or something.
Yeah,
So
yeah.
that I understood ki, yeah, because of the curvature of the space time. So it just follows the space time. So that is why. But like what if like if a light is traveling in a traveling perpendicular to a very high electric field, like super intense electric field, so wouldn't it like bend or something?
That's the thing, na? Like it, light is not going to like what light is going to follow. Light is just going to follow the space. So that field, or the, if we consider gravitational, is going to have on the fabric space time on which light moves. Light will follow that. You can never bend light. Okay.
So you, that means like by applying that electric field, you're just basically deforming the space time.
But like, how would electric field like bend light?
Like electric field or magnetic field, I don't know, because it is
Rishabh,
anyways yeah.
Rishabh, actually, electric field or magnetic field change the orientation of the light. I mean, polarization of the light. Not it can't bend the light.
Yeah, they wouldn't bend just simply. They wouldn't have the like, yeah, curve. When you put consider a Kerr-Newton metric, when you introduce charge to a black hole, some symmetry change. I don't know about Kerr-Newton that much, but yeah. And like what Kathan said, like it wouldn't change the light. It wouldn't bend light. It's just there.
Okay.
Were you talking about the interface, like bending, like the changing in the path at the interface of two media?
Not I don't know, I'm not
Dude,
sure.
when I say bending, I don't mean it like it can obviously change the angle. I'm talking about curve. Like bend means like, oh, okay, that's how you got this thing. When I'm telling bending, I don't mean like what I can say. I don't have my pen here. So this thing like angle change, okay, it's blur. So changing of angle is fine. I'm not telling that. When I say bending,
No,
okay,
I'm
that is,
not talking about the angle. I'm like, I
yeah,
was talking about
that curve
the,
basically.
yeah,
That,
literally
yeah.
curve.
It was like I got confused. That thing you cannot do. Like
No,
you
because
cannot
the
cross
idea
it.
I had now from is like, so basically I thought that like electric fields, you know, if I apply an electric field, so it might affect it.
Nah.
So like, is it like that light is only affected by uh, gravity or something, and not by other sort of fields?
How I would interpret is light is not even affected by gravity. Light is
Oh
just
yeah, you
there.
just
Yeah.
understood.
And what is light? Electromagnetic radiation, kind of that only. So how it like it's difficult to imagine, but they wouldn't have any effect on the like bending of light, both those things, electric field and magnetic field. Like Kathan said that. Basically, yeah.
But electric field is also a form of energy, na, and any form of energy will cause gravity, I guess.
Would that be that much? Obviously, if you are massive enough, you can also around you also light will never escape. But would that create that much energy or that much matter or that much mass which is required to have a like a substantiable bending of the space time? That is the question, and that cannot be produced by electric fields or magnetic field.
Then
But
actually,
it will actually change a little bit of angle, na? Means it should also deviate now from
No,
the.
that thing is possible.
Your stress energy tensor is different for an electromagnetic field, right? I'm just trying to remember this. Because you'd have to put the what's its name? There's a certain stress energy tensor. I remember the symbol F nu, and that's and then it yeah. I mean there is stuff like that, but yeah, I think
I
it
was very
does.
lucky. I didn't have to deal with stress energy tensor. So yeah, but yeah, I don't, because for the
GR
solid
is only a
particles,
theory of GR is only a theory of fields. You technically cannot have particles and all. You do have the fluid tensor, if I remember my GR correctly. But it's technically you. I mean, if you have particles, you have you have particles going around geodesics, and that's an approximation. But it's only a theory of fields. You can't really have potentials and all in it.
but it works.
If I remember correctly.
Chintan, does photons react with gravity?
That's what I'm telling now. This is how I interpret. Okay, I don't think so. A photon is ever reacting with gravity. It's the space-time which is it's following, and that's why it looks curved. At least that is what I feel, and I've read it also somewhere.
No, wait. But in the FRW metric, you do have photon pressure, bro. FRLW metric, you do have photon pressure as well. ऐसी बात नहीं है. I mean, individual photon is going to be obviously negligible, but you do have radiation pressure, right?
Yeah, but my question is whether
Bro, how does a radiation pressure connect the bending?
Because if you get radiation pressure, then it becomes part of the stress energy tensor, and that then in turn curves your space time.
There is a radiation pressure inside the sun as well. That is what opposes the collapse due to gravity. Okay, I don't think the radiation pressure has anything to do about the trajectory of the light.
I mean, for one photon, it's going to be not measurable. But if you look at the universe scale, I'm saying, then you'd have FLRW metric, and then it does affect it at a very tiny percentage.
So that is very, very tiny, and that you have to consider the whole universe. A black hole is like a small part.
But
so that
I mean, I don't think it's very. I mean, it depends on which stage of the universe you're at because of the cosmological constant and all. I don't remember my cosmology that well right now, but yeah.
But
I'd have to see. Yeah, go on.
The question is whether photon is affected by gravity. My question actually. I don't know actually. Whether photon
you need a quantum theory, na? You need a quantum theory at a photon level, honestly.
Okay.
Yeah, Chintan. Like for me, photon does not react to gravity.
Because you're in classical world.
Yeah, I do love the classical world and the relativity world which I am in. I don't want to go back into quantum field theory.
Okay, classically you want react, right?
Not classical, but the relativistic world, which right now I have been
because
in.
I don't know. I am in the process of learning.
Me too. I as I told you, I am dumb in the starting because there are a lot of things which I don't.
You guys are physicists. I am from engineering to physics.
Dude, you have more experience than us.
And my another question, you guys have talked about the negative energy. What is actually negative energy mean?
Exotic matter, na? That is just an assumption. That kind of matter is not found right now. Who knows?
Don't get me started about this again.
It's just I think it was proposed by Kip Thorne and his student to keep open the wormhole, and they hypothesized this type of matter. But the thing is, like when James Peebles hypothesized dark matter, it was practically observationally measured on a very large scale. We do have dark matter halos everywhere, but exotic matter was just something which happens out of nowhere. They have no practical proof of it. Like if you count Casimir effect as a practical proof, which I don't think so we should count, there is no another thing which we know, like negative energy density or that thing, because gravity will always be attractive. We have not found anti-gravity kind of a thing. So to keep open a wormhole, we have to use that concept of negative energy density. That is why Kip Thorne and his student, I forgot the name, they hypothesized this.
No. That's the thing is what I popped is if a negative energy exists, means the negative matter, I mean negative masses also exist, right? In such a way. If you think in such a way.
Yeah, negative and but have you like negative energy? Then you don't have like, and see, there are various meanings of negatives. Okay, when I say negative acceleration, it is like kind of deacceleration on a, so you can you imagine negative mass? What is a negative mass? Just imagine. Forgot about the repulsion of anti-gravity. It would do. What is negative mass? How can an object have a negative mass? You imagine that?
Yeah,
If you
I
can,
imagine it will work inverse gravity. It will repel each other.
which is
Like that.
required, na? So forget about
Ah.
inverse gravity and you like hypothesize negative mass. What
Ah.
properties would it have? You don't know. That is just a matter. You don't know.
Antimatter is negative mass, right?
What? Antimatter is not a negative mass.
No, antimatter is not a negative mass. It has pretty much
Because it has positron, which is a positive mass. Because the charge is only opposite.
Hello.
Questions on that box too.
I didn't see that. Like, I just like I don't like reading this things. What was that? Okay, we are learning about cosmology, Jay. We just learning that FLRW metric. We are on the very early stages. So honestly, I don't know about the relation of cosmological constant with this thing. What you are, so I'm still learning that. So my case was very primitive. Like all the GR I have learned is just through this 1 week project. I didn't know anything. So there are a lot of things which I have to do in very much details. Apart from this calculation, I've done like nothing about the cosmology, like the cosmological models, FLRW, all this. So I just have a descriptive knowledge about it, which I'll try to read and tell you.
Actually, then one more, my final doubt is
Yeah.
actually whether there is any relation between time dilation and time travel.
See, no, see, when there is time dilation, it is kind of time travel, right? Like, just hear me out, okay? When I say time travel, it's not time travel. Let's say you are moving very fast with the speed of light, not speed of light, little less. Best example, Interstellar. Consider Interstellar. So when they go to Miller's planet, for them it was normal, 1 hour, 2 hour. But for the what was his name, the guy who was in the spaceship, who was on that, yeah. So for him, 7 years would have had passed. So it is kind of time travel. For you, 3 hours have only passed. But when you return to a point, their time has been like, okay, here it is not 3 hours. Here it is like for 7 years or whatever calculation it might be. So I would consider that is as a time travel only. But like time travel. Then you have other things and which is not possible always, at least.
If we think through the entropy way, time dilation comes under time travel.
I honestly don't know about entropy and time travel, all this.
Because my perception says if you observe the time dilation means if any event going to happen. Example, you are going to break some. Okay, you have some glass part in your hand. You are going to break this glass part. If I am going to break this glass part means my from my point of view it is one time and another observer will observe it in another time, but anyway the event is going to happen. But in a time travel one observer can observe that event, another observer can't observe that event. I am thinking such. Yeah.
Did you say like in time travel, one observer cannot see that?
Yeah.
Why does that happen?
You can change that event. Actually, by time travel, you can okay, by travel by myself, I came from my future and make myself not to break this part. Like that, I can change the event so that another observer can't observe that event. Like that.
Oh, so which is why backwards time travel is not possible. We can travel further in time, we are doing it right now, but
But
we cannot travel backwards in time.
I'm
So
not talking
when
about
you're
the
saying
backward time
travel,
and all. I'm
yeah,
not relating that time dilation and time travel as a comparison because in such if you think through the entropy way, in time dilation for both the observer entropy should be same. But in time travel,
Wait, what?
entropy
Repeat. Can you repeat that line? Time dilation mein?
for both the observer entropy may be same. If you observe from if a time dilation is the property between two different observers in the different frame, right? But they are going to observe the same event from the different frame, so their time may be dilated, but the entropy may be same because the same event going to they are going to observe. But in the time travel, the entropy going to reverse, right? In that time travel.
You're saying in time travel, the entropy will go lower.
Yeah, it will be reversed.
Yeah.
If I am breaking
I mean,
that,
so usually
you are
when you
saying
do
time travel in which direction? Like backwards or
reverse
forward?
direction, we can take it as a reverse direction.
backwards.
Yeah, backward, the entropy would be reverse. But not, I am talking about negative entropy. Please keep in mind the positive entropy, but it going to reverse. If you enter, example, I am having one class, but again the same example. Its entropy is 2 means if I after I broken that part, entropy will become 3. If I reverse the time, again this entropy value 3 will reverse to 2. I'm talking about the positive plane of entropy only. If you take a negative plane of entropy means that Tenet movie, that is so different. Heat exchange
So honestly, you'll have to again get some of thermodynamics in your time travel. You're assuming that your time travel will not produce any entropy, and we don't have a quantum theory of gravity to talk about that.
I am not talking about it going to produce entropy.
But no, you're basically saying that you can violate the second law of thermodynamics if I time travel, right?
Maybe.
But that's what I'm saying. If you time, that just means this just shows that your argument should say that time travel should also produce entropy. And personally, I think it's quite possibly
it will
impossible.
reverse the entropy. Time travel may reverse the
Yeah,
entropy.
but even the event of even the event of creating in the process of time traveling, I'm saying you'd probably end up creating entropy, assuming this thing is possible in the first place. And that would increase the entropy overall, because I don't think any physicist would be happy if you destroy the second law of thermodynamics.
Yeah, we should get going. I am hungry. But yeah, this was the last one for this semester, at least now. Yeah, this month, Naja, we'll directly meet next month. Acha.
Okay, bye.
Yeah, me and Saurabh will skip that Friday as well due to exams.
Thank you so much for presenting this. It was actually really informative. And I loved everybody's question. Like at some point I lost track, but it was really interesting to see.
Thanks.
Thank you, Chintan, for this great session.
Thanks, man. Best of luck for your exams.
Chintan, thank you for your nice speech.
Yeah, thank you.
Yeah, it was a nice thing actually. Even your paper was nice. I was expecting all this.
Can you share your PPT, please?
Yeah. So one thing I didn't mention, like I've like if